Hello, everybody. Good morning, and welcome to the course Structured Property Relations. So, within this module, last week we have learned phonon, wave vector, first Brillouin zone, and we also discussed briefly the 7 crystal systems from cubic to triclinic. So, today we will discuss and learn lattice thermal expansion. So that means that what happens if we increase the temperature? If we change the temperature, then in any given lattice systems, cubic, orthorhombic, monoclinic, that it contracts, it expands. It expands in A, B, C direction. It expands in the A and B direction, maybe contracts in the C direction, and so on and so forth. In our daily life, even in the morning, if you boil water, then you also experience that when the temperature increases, the volume of the water increases. So in the liquid and gas system, it is very easy to see the change of the volume. But in the solid state system, the thermal expansion is very small, and within the naked eyes, it is very difficult to observe, unless otherwise the expansion is significantly very high. So it is very useful in science, in the solid state chemistry particularly, because for the material science, in any disciplines, thermal expansion and thermal expansion modeling is very, very important, and you agree with me. So we concentrate our thermal expansion coefficient, thermal expansion discussion today in the orthorhombic system. So what is an orthorhombic system? You have learned last week that in any orthorhombic system, you have A equal to not B equal to not C, and you alpha equal to beta equal to gamma equal to 90. If a system shows so-called positive thermal expansion in the orthorhombic system, then you will see that increasing temperature, you have A, B, and C all increases. And if you carefully look the slope looks like that in the A, B, and C direction is more or less similar. If the slope is similar, then we call it isotropic thermal expansion. What happens if the slope is negative? Then we call it negative thermal expansion. And again, the slope is similar. So this is again negative, but isotropic thermal expansion. And while you have system like this, the slope of A is different than slope of B and the slope of C. Then you clearly see the slope in the B direction is negative. So in the B direction, the thermal expansion of this orthorhombic system is negative. A direction positive, C direction positive, but nonetheless, if you carefully look at any given temperature, the slope is different. So now we learn how to calculate the slope, and it is so-called given a reference called thermal expansion coefficient. So concentrate on, for instance, you have A And here you have thermal expansion in, so you have initially lattice A1, with increasing temperature it is A2, then here it is your A2, here it is your T2, and here it is your T1. Then thermal expansion coefficient in A, so thermal expansion coefficient, so it is usually written in alpha. Then you can write with respect to reference point A1, then A2 minus A1, then minus Q. Usually in the solid state it is in the scale of 10 to the power minus 6 per Kelvin. So higher the value, then higher the thermal expansion coefficient, lower the value, lower the lattice thermal expansion coefficient. And importantly, if your value or thermal expansion is negative, then the system shows negative thermal expansion. And when you plot, for instance, temperature versus thermal expansion coefficient, then usually from, sorry, this is from 0 Kelvin, so it looks like this. So at very high temperature, it should saturate. A question arises whether the system in all A, B, and C direction shows negative thermal expansion. Indeed, it is possible. These systems in nature are quite rare, but nonetheless, it is possible that in all three dimensions you have thermal expansion coefficient negative, followed by that your volume or cell volume lattice thermal expansion is negative. Thank you. And now we'll learn so-called the isotropic thermal expansion and anisotropic thermal expansion. In orthotropic system, again, if all slopes are similar, yeah, so A, B, C, that means your alpha A, alpha B, alpha C at any given temperature is alpha A equal to alpha B equal to alpha C. We call it isotropic thermal expansion. But the system, like, let's say in one direction it is negative, in the B direction, A direction it is positive, C direction it looks like this, then clearly that at any given temperature, so alpha A equal to, not equal to alpha B, not equal to alpha C. It is so-called, this system is so-called anisotropic thermal expansion. So in the anisotropic thermal expansion system, you can also calculate the degree of anisotropy, which should be more than 0. It is so-called anisotropy thermal expansion anisotropy. That means it is sometimes written A modulus alpha A minus alpha B plus modulus alpha B minus alpha C plus modulus alpha C minus alpha. So if the value shows 0, isotropic thermal expansion. If the value shows more than 1, it is an isotropic thermal expansion. Any question, please? If this is not the case, thank you very much. I'm sure that you have learned thermal expansion coefficient,